Welcome back to the CryptoSec Ed channel. In part one, we looked at some simple functions, simple Python code scripts to demonstrate the difficulty of hashing values that have a value lower than a given target, how we can specify that to try to get a specific rate, how to generate random transactions, and how to generate a very simple hash chain. So this is the code for the hash chain. Again, we're using the same function to generate the hashes, generate the hex digest of any string. And the code itself, again, is very, very simple. These scripts are very short, very simple. We just print some welcoming messages, open up a file, getting ready to write to it. If any response is just a letter N, either uppercase or lowercase, we quit. Otherwise, we open the log file, read to the last end of the file, hash the last line, and then enter into that, append to that file that hash and the last response from the user. Okay, so we can verify any log file. So if I type the log file as it is, we can check, run the C5 code. It's just going to tell us that the log file is intact, no changes have been made. We can see what the code is doing. It's reading in the log file. It ignores the first line because there's nothing to check on the first line. It's always going to be the same value. We can't hash the previous line in the first line because there is no previous line. But for every line after that, we read the line in, split it into the hash and the rest of the text. If the hash of the previous line of the log doesn't match the hash we've read in, then we know something has gone wrong. We print these warning messages, and if we go through the whole file and no errors have been identified, then we can say it's intact. If we have found any problem, we can see it will print the error. So let's just try this ourselves. I can add a single character to the log file, and I run the verifier. It will tell me that there is a problem with this line. Because hashes aren't the same as error correction or error detection, we don't know what the change is. We just know that there has been some change made in the file. If I run again with that change undone, that's fine. If I change one of the hash values, again, it's going to say something went wrong. And if I undo that change, everything is correct. And if I try to erase a whole line, that is going to break the hash chain. And again, that is identified as something has gone wrong. So that is our very simple hash chain generator and verifier. Now, it is important to say that hashes are not actually secure cryptographic functions. They are public. SHA-256 is something anyone can calculate. So this log file this is not actually secure in any meaningful way. If you were to set up this log as a something that you wanted to prevent anyone from tampering with, this is not how you would do it, because anyone can generate a hash function. I can change a message here, change a character, calculate what the hash is supposed to be, and then update this subsequent hash. I can delete lines and generate myself what the hashes should be and fix that. If you when we put this together to make a blockchain, we need to include the proof of work in order to make it something that is difficult to forge, difficult to recreate. Okay, so we're now ready to put some of these things together and generate a very simple blockchain. So we're going to use our function to generate hashes. We're going to be using that quite a lot. We've got some placeholder transactions, some things we want to put in the blockchain, we want to protect. We have an additional function here. This is just something to append something to a file. And then we've got the main body of our function. So let's go through it line by line. So we're going to start with specifying a single file to be the blockchain. So in practice, the Bitcoin blockchain exists on many computers over the internet. So part of any blockchain code needs to be how these different computers synchronize files, send back and forth data from the blockchain. We're dealing with everything's running locally on a single file, everything's saved in a single file, so we don't have that complication. And we've got a base text here. I'm saying this is the CryptoSec Edge blockchain. If you want to run this yourself, you can change this to whatever you want. And we're going to generate a Genesis block. Again, we're going to put in previous hash as a sequence of 64 Fs because when we start off, we don't have anything previous to hash, so we don't actually use the real hash the first time. I've manually set the challenge here to be, again, something that will cause blocks to be found roughly every 2 seconds when a single miner is running. If you're running this yourself and you want to have the same rate, you might have to tweak that a little, including if you're running more than one miner. So it's basically the same difficulty as we used in the fixed difficulty code. So we've got another infinite while loop. We're generating random numbers each time through this loop. So we start with a bunch of a set of transactions, a transaction that is randomly generated that we want to include in the blockchain, along with the base text we're using in this blockchain. And then for each time through the loop, we come up with a random nonce, a number used once, random number in this range. We combine the base text, the random transaction, and this nonce, and we then generate a hash of the previous hash, the previous block, with this test string. So those two lines are hashed together. If the hash produced is lower than the difficulty, then this is basically us finding a new block in this blockchain. If it's bigger, we ignore it and carry on. So this is the thing that is going to happen very rarely in the iteration through the loop, but again, we're hoping it's going to occur once every 2 seconds or so. So we're doing some calculations, updates the count, how many blocks we've found so far, how much time has elapsed since we start. This is just to present some information to let the user know what's happening and what sort of rate these are occurring. We're printing out these values, the hash and the input to the hash function, printing all these values out, and then we're updating what was known as the previous hash. This was the previous hash of a input that satisfied that difficulty challenge. And we're also generating a new transaction so that we can add a different set of transactions to the blockchain. So if I run this code now, Python C6, it will start running away, generating blocks, doing lots of hashes of different random values. You can see the random nonces here, and eventually it is generating some valid blocks. And this will keep going as long as we want, as long as we want to run it. And I can open up the value here, simple blockchain.txt, and we can see all the different hashes, all the different nonces, all the transactions that were used to generate this blockchain. So we can verify any of these. So again, look at the code, see what's happening. Any test string is going to consist of the base text, the random transaction, nonce, and then the previous hash. So if I copy any example like this and copy that and put it into SHA-256 and generate the hash. I've apparently made a mistake. Let me try that again. Let's see. Try this. There we go. Sorry, it's I got them in the wrong order. It's the hash first, and then the text of the transaction and the nonce. So we can see the hash of all this produces value 00000076 GC, 76 DC, 97080, 97080. And we can manually check all these all the way down. So yes, block contents. Yeah, the actual hash function here, you can see it's hashing the hash of the previous block first, and then the base random transaction and the nonce. We got the order the wrong way around there. Okay, so for a single instance of this code running, this is fine, but obviously blockchain is meant to be used by multiple participants, multiple miners at the same time. So what I've included in this last piece of code is text for the miner to code for the miner to enter their name. And so every time they find a block, that the identity of that miner will also be included in the transaction details that are hashed. Also, this code just produces the blockchain. It doesn't do any verification. What I've added here is code to verify the blockchain. So just like we verified the hash chain here, we've got similar code to verify the blockchain, verify that hashes match in that chain, the chain is not broken, but also, as well as verifying the hash chain, we're making sure all the hashes satisfy that difficulty. So all of the hashes satisfied the proof of work. They've enough computing effort has been put in to produce those that they got a hash lower than the challenge difficulty. Again, when I said previously that a simple hash chain doesn't have any inherent security because it is just using hashes with no keys, there's no secrets involved. The security of the blockchain occurs because the amount of computing power needed to generate these hashes is so immense that anyone trying to fake a block or modify transactions in the past would have to redo so much effort that it's not computationally worth it. It's not financially feasible. Okay, so we've got a new piece of code. We can have multiple miners running. We can have them running in parallel, and each time someone finds a block, what they do is they first verify that someone else hasn't already added another block. So every miner is going to read the blockchain, verify that it's correct, and then store that last hash, and then start adding a new block onto that using that last hash. If two miners find a block in a similar period of time, one of them is going to update the blockchain first. When the other one then tries to update the blockchain, they'll need to make sure another new block hasn't been added. And if it has, they have to basically throw that block away and start again from the new hash. So we can show this in practice. I'm going to have Alice running here, doing a new, starting a new blockchain from scratch. I'm going to go to simple and run C7. Bob run as well, and what we'll see is Both of them are trying to find valid blocks. Each time they find a block, we can see they're verifying the blockchain. Bob found a few blocks there, and then we saw Alice was trying to find a new block. Alice had found another block, but was too slow. Bob had already updated for a new hash, so sometimes their efforts do get discarded. We can cancel these and start them up again. And each time they start, they will verify the blockchain and just carry on, add on to the end of that chain. And we can see everything gets verified, all the nonces are stored, and all the hashes are satisfying the proof of work hash. So obviously this is not a fully formed blockchain. Even as a demo, there's a lot of details missing. These transactions are random, and there's no check on the verifying the transactions. A very important part of the work of the miners of the blockchain is to make sure all the transactions are valid. Someone is not trying to spend Bitcoin they don't have, or giving themselves an amount of Bitcoin out of nowhere. So all the transactions need to balance. Everyone can only be spending cryptocurrency that they have. So that is obviously something that would need to be included. Obviously, this is operating locally, running it as code that's meant for a network with multiple participants on the network would be a huge deal. And I think it's necessary for just a little demo to demonstrate the concepts. Obviously, an important part of security is you generally try to avoid rolling your own. So using this code as a basis for an actual blockchain is not a good idea. This is purely meant for education, to understand the concepts and to play around with them. I've made the code available on GitHub, but I would be shocked to see anyone trying to come up with an actual blockchain based on this. This is also a proof of work blockchain. There's plenty of other types of consensus mechanisms available. Proof of stake is also very popular, and that works on a very different concept. But this includes a lot of the details of a very basic Bitcoin, very basic blockchain. So you're welcome to explore the code, have a look at it, play around with yourself in your own time. That's all for this video. In the next video, I'll be going through some other security tools I've developed over the course of my career.